Today I want to talk about two more types of nuclear reactions, both of which can result in transmutation. We've talked about radioactivity and some specific types of radioactivity: alpha decay, beta minus, beta plus, gamma decay. Today we're going to talk about nuclear fission and nuclear fusion. Two more types of nuclear reactions, but these ones aren't quite as natural, aren't quite as spontaneous as radioactivity. First thing we're going to talk about, nuclear fission. How many people take biology here or have taken biology? You learned about mitosis in biology, right? Sometimes mitosis is referred to as cellular fission. Anybody ever heard that term, cellular fission? Yes? What does that mean? What is mitosis or cellular fission? Go ahead. When cells splits up, right? So when you got one thing that splits up into two. Nuclear fission is when the nucleus splits up, when one heavy nucleus splits up into a couple lighter nuclei. You can see in the example, that's what we have here. Uranium-235 splits up into krypton and barium. There's a bunch of combinations that it could split up into. This is just one that I picked to write down as an example. This is far from the only example of nuclear fission that we could have. Okay? But it's one. One heavy splits up into two or more lighter nuclei. Now, there's some other things here as well, these neutrons and some energy. We'll worry about that in a minute. Let's worry about the big nuclei first. One splits up into two. So we'll define it as one heavy nucleus splits up, just like one cell splits up into two cells. One heavy nucleus splits into two lighter nuclei. I don't want to say light nuclei because they're not necessarily light. They're lighter than the first one, than the one that we started with, than the parent nucleus. There is some other stuff there. There's some neutrons there. Why are they there? Why can't we just have this uranium-235, krypton and barium, or whatever combination it happens to be? Because uranium-235, if left on its own, would take way too long to decay. We don't want to wait that long. So we kind of coax it, prompt it into happening. It's the iceberg analogy that I gave you yesterday, right? You get the iceberg in the North Atlantic and you smash the Titanic into it. The iceberg is ready to break apart. Okay, you hear it cracking. You feel like there should be a chunk of ice breaking off at any time, but it's not breaking off. So what do? You hit it with something, and then the chunk of ice breaks off. Okay, this uranium-235, it's like it wants to break up, but it isn't. So what do? We hit it with a neutron. We bombard it with a neutron. And for a brief moment in time, that neutron actually gets absorbed by the uranium-235. It actually becomes, for a short time, uranium-236, which decays into, among other possible combinations, in this case, krypton and barium, and then a few more neutrons and some energy. A lot of energy? Well, relatively speaking, compared to a chemical reaction, a lot of energy. If one single uranium-235 nucleus decays into krypton and barium, it'll generate enough energy, about enough energy, to move a speck of dust. Doesn't sound like a lot, but we're talking about a single nucleus reacting. That's a lot of energy, actually, when you're talking about a single nucleus generating enough energy to move a speck of dust. Now, if we want to power a city by a nuclear power plant, or we want to blow up a city, in the case of a nuclear bomb, you got to move a lot of specks of dust. So you got to have a lot of these reactions taking place. It's not very efficient to fire billions of neutrons at billions of uranium-235 nuclei and expect this reaction to power a city. So what do? Well, it works out pretty convenient, actually. You need a neutron to be absorbed by the uranium-235. But conveniently, in this particular reaction, there's 3 neutrons produced as the products. Sometimes there's 2, sometimes there's 4. In this one, there's 3. Those 3 neutrons if the conditions are right, those 3 neutrons can be absorbed by 3 more uranium-235 nuclei. So you got the first reaction, now you got 3 reactions. Well, they're going to produce 9 neutrons, which are going to cause 9 reactions, which are going to produce 27 neutrons, 27 reactions, 81 neutrons, 81 reactions, 243 neutrons, 243 reactions, and so on. This is what we call a chain reaction. When the products of one reaction cause more reactions. And in this case, the products that are causing the more reactions are the neutrons. The amount of specks of dust that would be moved grows exponentially, so that within a fraction of a second, there's enough of these nuclei that are splitting up into krypton and barium and releasing enough of these specks of dust worth of energy that you could blow up a city, literally within a fraction of a second. It happens so quickly. The bomb that the Americans dropped on Hiroshima in 1945 was a uranium bomb. They used what was called enriched uranium. Okay. Naturally occurring uranium isn't fissionable. Naturally occurring uranium is something like 99% of non-fissionable uranium. So what they had to do in the 40s was separate the bad stuff from the good stuff, the 99% bad stuff from the little bit of good stuff. And they had to get enough good stuff to undergo nuclear fission and produce a bomb. They needed about 50 kilograms of it. It took them several years to separate 50 kilograms of uranium. The bomb they dropped on Nagasaki was a plutonium bomb. It wasn't the same type of bomb at all because they didn't have enough uranium. They didn't have enough. Simple as that. They didn't even test the uranium bomb. They just trusted that it would work because they didn't have enough uranium to test it. If the uranium-235, this fissionable uranium-235 is set up so that it will react or absorb these extra neutrons, then you can sustain this chain reaction. In the nuclear fission bomb in 1945 that they used, the uranium bomb that they used in 1945 when they bombed Hiroshima, it consisted of about 50 kilograms of uranium. It blew up a city. But there was only actually about 3 or 4 or 5 kilograms of that uranium that actually exploded. About 90% of it was actually wasted, never actually exploded. The reason for that is because this explosion grows so quickly, so exponentially, within a tiny fraction of a second, that the bomb actually blew itself apart before the other 45 or so kilograms of uranium could absorb neutrons. Does that make sense? They had to have the 50 kilograms of uranium to make this thing work, to make the 5 kilograms explode. They knew the other 45 wouldn't explode. But they had to have it to make the 5 explode. But still, 5 kilograms, or less than 5 kilograms, caused the city to blow up. Yep. Yeah, I'm not sure that they had a prediction well, they would have had a prediction as to how much would explode. I'm not sure that they knew exactly how much would explode. I don't think we know even to this day exactly how much exploded. But we know that the vast majority didn't explode because the bomb would have, they would have known ahead of time that the bomb would blow itself apart before it even had a chance for most of it to explode. So it was predicted, not necessarily the exact amount, but it was predicted what happened. Yeah. It's a good question. It's the shape. Essentially, we use a neutron gun to fire the first neutron at the uranium-235. and then it's essentially the shape of the bomb that causes the neutrons, the extra neutrons that are produced to fuse with uranium-235. I mean, I say it's difficult. It's like getting uranium-235 is incredibly difficult to get. Right? I mean, that's why, everybody's worried about nuclear bombs and terrorists, right? We don't really have to worry that much about nuclear bombs in the hands of terrorists. I mean, it's not impossible, but it's not likely, because the two types of fission bombs that we have, uranium and plutonium. Uranium is very, very difficult to get, enriched uranium. It took the Americans 3 or 4 years to get 50 kilograms of it, right? It's hard to get. It's hard to make. Okay, North Korea, Iran have had enriched uranium programs, and the Americans want to shut that down, obviously, for obvious reasons. But even if they don't, it's still difficult to get enough to build a bomb. But all you have to do once you do that, once you get the enriched uranium, is design your bomb in the right shape, and it's not actually all that difficult to build it. I mean, it would be difficult for you or I to build it, but not difficult for nuclear engineers to build it once you get the uranium. But it's hard to get the uranium, so that's the good news. The other kind of bomb, plutonium, is actually pretty easy to get. Plutonium is quite easy to get. It's a product sometimes of nuclear power plants. But the good news is the bomb is very technically difficult to build. So it's kind of with either type, there's something that makes it difficult. That's why we don't have to worry too much about the terrorists, unless they happen to get one from, unless they happen to buy one that was already made from somebody, right? Sorry? So where does the energy come from? This 200 mega electron volts, this energy that moves the speck of dust right here, where does that come from? Well, the nucleus splits up. That's where it comes from, right? Well, yeah, but why? Why, when the nucleus splits up, does it generate enough energy to move a speck of dust? Or when you get an exponential number of these nuclei splitting up, why does it generate an exponential amount of energy? Because of this concept they call mass defect. When a nucleus splits up, mass disappears. And that might seem odd, because the law of conservation of mass, or the law of conservation of matter, says matter can't be created or destroyed. Who told you that? Who said matter can't be created or destroyed? Was it Mr. Real? He lied. Matter can be created, and matter can be destroyed. In the case of a nuclear reaction, matter's gone. Like, there is literally missing mass. Mass disappears. Mass defect is the difference in mass between the products and the reactants, or the missing mass. The products and the reactants, or the parents, the daughter nuclei and the parent nucleus. The difference in mass, the mass lost. So why would Mr. Real lie to you? Well, because that's what teachers do sometimes. We do lie to you sometimes. We lie to you when necessary. When you're talking about chemistry, mass isn't destroyed, or it isn't created. What would be the point of telling you about something that involves nuclear physics when you're not learning about nuclear physics? So yeah, he kind of lied to you, but yeah, it was one of those lies he had to tell. Mass can disappear. I told you last year in Physics 20, Mr. Coderre told you last year in Physics 20, energy can't be created or destroyed. We lied. Energy can be created or destroyed. It can. You can make energy, but not from nothing. You can make energy from mass and mass from energy. So what it really should be is not the law of conservation of mass or the law of conservation of energy. It should be the law of conservation of mass / energy. Because if one goes up, the other goes down. If one goes down, the other goes up. This missing mass, this mass that disappears, gets converted to energy. That energy right there, the missing mass becomes energy, and that's why you get so much of this energy produced. By the way, does anybody know the relationship between the mass and the energy? All of you should if you think about it. Okay, equals mc squared. The energy that's released is equal to the mass defect, the amount of missing mass, times the speed of light squared. And because it's the speed of light squared, 10 to the 8 squared, you can imagine it doesn't take very much mass at all to be missing in order to generate a tremendous amount of energy, to move a lot of specks of dust, to power a city, or to blow up a city. Let's talk about that other kind of reaction now, that other kind of nuclear reaction, nuclear fusion. Fusion, fusing, when two nuclei, two light nuclei, fuse together to form one, I don't want to say heavy, because you can see in the example that I got here, that's not heavy. It's helium. It's still light, but it's heavier. The example that we have here, hydrogen 2, that's a heavy isotope of hydrogen. That's not the normal isotope of hydrogen. Regular hydrogen is 1 proton, no neutrons. Heavy hydrogen is 1 proton, 1 neutron. You can make water with heavy hydrogen. Do you know that? It's called heavy water. I remember growing up, I grew up about 2 hours away from a nuclear power plant in New Brunswick. I remember a couple of times hearing on the news about something about heavy water. I don't know what it was. I don't remember details of it because I was little. But I was old enough, I remember, to know that water was H2O. I didn't know anything about chemistry, but I knew that water was H2O. So I remember hearing, one time I remember hearing about heavy water and thinking, oh, what's heavy water? It must be H3O, right? Heavy water's got to be H3O. It's got extra hydrogen, right? That makes sense. Of course, even if you could get this compound, it wouldn't be water, right? It would be something else. Heavy water is H2O, except it's H that's heavier. It's not regular hydrogen, it's heavy hydrogen, deuterium, we call it. Chemically, it's identical to regular water. It's just heavier than regular water, that's all. So here's what happens in nuclear fusion. You got two light nuclei combining to form one heavy nucleus. Remember over here, we had one heavy, two lighter. Over here, we have two lighter, one heavier. Now, just like in the fission one, you got some extra stuff in there too. The neutrons, the energy. Here we got a neutron. We got some energy produced. But the main part of this equation is the two lighter nuclei fusing together to form one heavier nucleus. In that process, we get a mass defect. We get missing mass. Mass disappears. It gets converted to energy, gets released, and there it is. So how do we get a chain reaction with fusion? Fission, you can see how the neutrons can react with more uranium nuclei to cause a chain reaction. We don't need any neutrons for this. How do we get more of this to happen? How do we get this to grow exponentially quickly? Blow up a city or power the sun. This is what happens at the sun, right? Nuclear fusion. The main power source of the sun. Here's the thing. Hydrogen, that hydrogen nucleus is positive. So is this one. As they get closer and closer together, there's a force of repulsion. As they get closer, that force becomes bigger and bigger and bigger and bigger, to the point where these things get really, really close together. That force of repulsion is massive. They don't want to join together because of that massive repulsive force. So you gotta supply a lot of energy to overcome that repulsive force. That energy is usually in the form of heat. So we get energy on this side as well. You put a lot of energy into this. You overcome the repulsive force. They fuse together. Mass, poof, disappears. We produce helium, a neutron, and obviously more energy on the right side than we have on the left side. Otherwise, it wouldn't work out very well. How do we sustain it? Well, some of this energy goes back into making more hydrogen fuse together. 1945, the Americans had two types of bombs, right? Both fission, uranium, plutonium. They bombed Japan. In 1952, the Americans developed the H-bomb. The H-bomb was this. They've never used that in wartime. Tested it, but never used it in wartime. This bomb was so powerful, way more powerful than anything was dropped in Japan. This bomb was so powerful that the energy source that actually kick-started it, the energy source that actually fused the original hydrogen together, that kick-started it, was actually a fission reaction. So it's kind of like, you know what, let's sacrifice this just to get us a little bit of energy to kickstart this. We need a lot of energy to make this happen, but we get a lot more energy out of it than we put into it. Yep. How does the sun sustain it? That's the power source of the sun, right? How does the sun sustain it? The sun's hot. It's a lot of energy. All that hydrogen in the sun has very little trouble overcoming the repulsive forces because of the heat, massive amount of heat in the sun. Make sense? Question? No? Okay, let me define a couple terms here, and then that's going to be it for us here today. Mass defect we've already defined. We're going to write down that definition again, but we're going to give you a second, seemingly different definition, but not really different. I'll explain that in a second. We define this other term called binding energy. Mass defect, the difference in mass between the reactants and the products. That's the definition that I already gave you, basically, right? The missing mass. When this reaction takes place, you lose mass. Not destroyed exactly, it's converted to energy, but you lose. The mass isn't there. Now, the other definition for mass defect that I'm going to give you, which on the surface doesn't seem to go with this, but does. It actually, the next definition actually causes the first one. The second one is responsible for the first one. And if this seems a little odd to you, the idea that you can lose mass in this reaction, this one's going to seem odder. It's the difference in mass between the nucleus and the nucleons. A nucleon, proton, and neutron. So what we're saying here is this. If you take the mass of the rest mass of all the protons and all the neutrons in a nucleus, and you add them up, you get a certain mass. Well, you should get the mass of the nucleus, right? But you don't. The mass of what makes up the nucleus is different than the mass of the nucleus itself. It's like saying there's 30 people in this room. If we add up the mass of everyone in this room, we should get the mass of the room. There's a missing mass. We call it mass defect. And that's what causes this. That's what causes the difference in mass between the reactants and the products. This missing mass, this mass defect, is responsible for this, the binding energy, which we can also define in a number of ways, but we'll only define it in one way, the way that we need to define it for our purposes. We're going to define it as the energy released in a nuclear reaction. And we can find that binding energy, the energy that's released in the nuclear reaction, by multiplying the mass defect by the speed of light squared.